Hi. Now, in today's class, we will go through the types of hybridization. Before this, we have understood in detail what is hybridization. Now, we'll look into the types of hybridization. In this lecture, we will be looking into hybridization that contains only s and p orbitals, right? Because there are type of hybridization that contain even d orbitals, right? We'll be covering that in a different lecture, right? So here, types of hybridization containing s and p orbitals, right? So we have three types of hybridization: sp hybridization, sp2 and sp3 hybridization, right? We'll understand this in this lecture in detail. First, let's just do a quick recap of what is hybridization, right? Hybridization, firstly, it's mixing of orbitals, right? When different orbitals of outermost shell, right, of valence shell mix and merge, right, and they redistribute their energy, right, to form a new set of orbitals which we call as hybrid orbitals, right? Now, the second thing is, this is your definition of hybridization, right? Now, there are two things in hybridization. First is your promotion concept, right, when an electron from a filled orbital would be promoted to a empty orbital, right? And from where does we get the energy, right? Energy is an energy to promote this electron from filled to empty orbital will come from the attractive interactions. When two atoms will come close to one another to form a molecule, right, there would be attractive interactions, right? Now, due to this attractive interactions, energy would be released, and this energy would be used to promote this electron from a filled orbital to an empty orbital, right? So, first thing, what we will be doing here in hybridization is, first we will write the ground state electronic configuration of atom, right, of atom that will undergo hybridization in the molecule, in the covalent molecule, right? Then you will write the excited state electronic configuration. Now, excited state electronic configuration is that in which the electron would be transferred from the filled orbital, right, to the empty orbital of the same shell. Remember, of the same shell, because this hybridization of orbital will take place between orbitals of nearly same energy, right? It's not that 1s orbital will mix up or hybridize with 2s orbital. No, if you have two shells, right, then 2s and 2p orbitals will mix and merge, will hybridize, right? Or what we say is that the orbitals of the same shell will hybridize, right? Because hybridization can take place only between those orbitals that have nearly same energy, right? Energy difference should not be much, right? So you write down the excited state electronic configuration, right? Once you have the excited state electronic configuration, then merging of orbitals will take place, right? And when this merging of orbitals will take place, hybrid orbitals will be produced, and the number of hybrid orbitals that you get as a result of merging would be equal to the number of atomic orbitals that undergo merging, right? So, as a result of merging of orbitals, you get hybrid orbitals, right? For example, if suppose one s and one p orbital mix and merge, right, then since two atomic orbitals s and p orbital merged, they will form two hybrid orbitals, right? So the number of hybrid orbitals formed would be equal to the number of atomic orbitals that have undergone merging, right? So merging of orbitals, right, it will give you a new set of hybrid orbitals, right, that have same energy and same shape, right? Let's write it over here. They would have same energy and same shape, right? Now there are certain things that we need to know for hybridization, that when hybridization will take place, it's not that all orbitals will undergo hybridization or all half-filled orbitals will undergo hybridization. No, even some orbitals may remain unhybridized, right? We'll be looking into this when we'll study the structure of ethene and ethine, right? In ethene, one orbital will remain unhybridized, and in ethine, that is acetylene, two orbitals on each of the carbon atoms will remain unhybridized, right? And these unhybridized orbitals then undergo interaction, right, on both the carbon atoms in ethylene to form pi bonds. We'll understand that in a different lecture, right? So here new set of hybrid orbitals would be formed, and also in the same in the same shell, right? It's not that only half filled orbitals will only take part, even completely filled orbitals can also take part. For example, in ammonia, even the completely filled, right, orbital, which is 2s2, also take part in the hybridization, right, of nitrogen atom, when nitrogen atom will undergo hybridization when formation of ammonia takes place, right? And that filled orbital, right, would be shown as lone pair of electron. That's what the lone pair of electron we call. That lone pair of electron is nothing but the filled orbital that have taken part in hybridization, right? And hybridization will never occur for atoms, right? It will never occur for atoms. Why? Because we have a promotion concept, excited state electronic configuration, and this promotion will only take place when two or more atoms will come close to one another, as a result of which energy would be released and an electron would be shifted from filled orbital to the empty orbital, right? So hybridization is the concept only in case of compounds, when the formation of covalent compounds take place. It does not occur in atoms or in single atoms, right? So let's write it over here. And the shape of hybrid orbital would be that of, because we would be drawing these structures when we study hybridization in different compounds, we have to draw these hybrid orbitals, right? So hybrid orbitals, it will look like this. It looks like a p orbital, right? But one of the lobe is bigger, the other lobe is very small. It's like this, right? And this bigger lobe would always be the positive lobe and the smaller lobe would be the negative lobe, right? This is how you will represent the hybrid orbital, right? This is your hybrid orbital, right? And hybridization, this is important point, hybridization occurs only in compounds, right, not in atoms. We have discussed the reason for this, because we have a promotion concept in hybridization, and promotion will only take place when compound formation takes place, and during compound formation, when two atoms will come close to one another, energy would be released due to attractive interactions, and this released energy will move electron from the filled orbital to the empty orbital, right? So these are important things, right? These are important points of hybridization. Now let's just quickly see this SP, SP2 and SP3 hybridization, right? SP hybridization is when S and P orbital of the same shell, right, will mix and merge and redistribute their energy to form a set of new orbitals known as sp orbital, right? When one s orbital is represented like this, when one s and one p orbital, right, will mix and merge, and these two will redistribute their energy, right, to form a new set of hybrid orbitals that will have same energy, right, here, that will have same energy and same shape, right, and will have a definite shape also, right. It will form hybrid orbital of this sort, right. This is your sp orbital, right, and they would be 2sp orbital and would be represented like this, right, because I said one of the lobe is bigger, the other is a smaller lobe, right. So this is the smaller lobe of this and this is the smaller lobe of this, and it will always be, the bigger lobe always be positive, right. So this is your sp hybridization, right. So one s, right, and one p will mix and merge and will redistribute the energy to produce two set of hybrid orbitals that will have same energy and will have same shape, right. This is your sp hybridization. Now let's take an example of sp hybridization. The example is beryllium BeF2, right. The example is beryllium fluoride, right. In beryllium fluoride, let's look, atomic number of beryllium is equals to 4, right. This is the atomic number of beryllium. So we will be writing the ground state electronic configuration first, right. So ground state electronic configuration would be 1s2 and 2s2, right. Now we have, if you look here, 2px empty orbital, right. Now we will be writing excited state electronic configuration. When in excited state electronic configuration, right, when beryllium fluoride will form, beryllium and fluorine atoms will come close to one another, right, and there is an attractive interaction like what we have studied in covalent bonding. Due to this attractive interaction between beryllium and fluorine atom, energy would be released, and this energy would be used to shift electron from this filled orbital to the empty orbital, right. So excited state electronic configuration would be 1s2, 2s1 and your 2px1, right. This is your excited state electronic configuration. Now mixing and merging will take place, right, like this. So you have s and p orbital, right, half filled s orbital and half filled p orbital. Now mixing and merging will take place between orbitals of nearly same energy, right, and nearly same energy orbitals would be of same shell. You can see this s and p orbital belongs to the same shell, second shell. 2s and 2p means it belongs to the second shell. 2 represents, what does 2 represents? 2 represents the principal quantum number, right. So mixing and merging will take place between these two orbitals, same as this, right. One is s like this, the other is p like this, right. They will form sp or two sp hybrid orbitals of this form, right. And with those sp2 hybrid orbitals, these two fluorine atoms will hybridize, right. So we'll just write it like this. So it would be same as this, 1s, this 2s, right, and this 2p will form like this. Like this, right? This is your two SP2 hybrid orbitals. These are SP hybrid orbitals. These are two SP hybrid orbitals, right, which are oriented at 180 degree to one another, right, like this. These two orbitals are oriented at 180 degree to one another, right? Now this hybrid orbital in the formation of BeF2, this hybrid orbital, right, each of the sp hybrid orbital will overlap with each of the fluorine atom, right, to form BeF2. We know that the electronic configuration for fluorine is 1s2, 2s2, 2px2, 2py2, 2pz1, right? Now let's look at the formation of this compound, right? This is your sp2 hybrid orbital, s and p, right, which are singly filled orbitals, right? So it contains electrons like this, right? So we have two fluorine atoms, right, in BeF2. So two fluorine atoms, it's like this. Two fluorine atoms will overlap with sp hybrid orbitals of beryllium. Beryllium has undergone sp hybridization, right? It's like this. Right? This electron should be of opposite spin, right? Both the electrons in the half filled orbital should be of opposite spin, and it would be like this. Like this, and here you have angle of 180 degree, right? So here beryllium atom has undergone sp hybridization, right? And what would be the shape, since these two hybrid orbitals are inclined at 180 degree to one another? So this is your linear shape molecule, right? This is for beryllium, right? And this is for, these two are for fluorine, and this is your beryllium. So this is your linear shaped molecule. Linear shaped molecule, right? This is it. If you quickly look at it from VSEPR theory perspective, if you want to explain the shape of BeF2 based on VSEPR theory, we know that beryllium has 2 electrons in its outermost orbit, right? It has 2 electrons in the outermost orbit, right? And fluorine has 7 electrons in the outermost orbit, like this. So this is how sharing of 1 electron will take place, right? And a molecule is formed like this, right? So these are two bond pair of electrons, right? These two are bond pair of electrons, and as per VSEPR theory, these two bond pair of electrons will repel one another, right? And will try to move as far apart as possible from one another, right? And when they will move as far apart from one another as possible, then they will so that there is no further repulsion, right? These bond pairs, right, due to repulsion, right, will move far apart from one another and will take these positions, right? Will take these positions that will make it linear molecule, right? These two bond pairs will acquire positions, right, so that there is no further repulsion, right, that will make this molecule linear. The position of bond pairs, right, is such that the molecule is now linear, right? So as per this also it's linear, and as per this also it's linear. So whenever using hybridization, if you know the hybridization of the central atom, you can tell its shape, the shape of the molecule, which suppose here you have BeF2, the Be molecule, beryllium molecule, has undergone sp hybridization. So since sp hybridization, right, in the sp hybrid orbitals are always linear, so the molecule is linear, right? So if you know the if you know the type of hybridization of the central atom, you can tell the shape of the molecule, right? Now let's look at the other example, SP2. Here 1s, right, 1s and your 2p orbitals will mix and merge, right? 1s and 2p orbitals, it's like this, will mix and merge to give you 3 set of hybrid orbitals. Maybe this is, say, py and this is your px, right? So these are 3 orbitals, right? So 3 orbitals, when 3 orbitals will mix and merge, say this is px, say this is py, when 3 orbitals will mix, they will form set of 3 hybrid orbitals, right? Because number of hybrid orbitals would be equal to the number of orbitals undergoing mixing or merging, right? So it would be like this. The hybrid orbitals, SP2 hybrid orbitals, will look like this. It will look like this, right? You have to show the small lobe as well. It will look like this, right? And these are 3 set of SP2 hybrid orbitals, right? And these are directed at an angle of 120 degree from one another, right? SP2 hybrid orbitals are directed at, the angle between them is 120 degree, right? And their shape is triangular planar, right? Since the angle between the hybrid orbitals, these 3 hybrid orbitals, is 120 degree, so the shape of the sp2 hybrid orbitals would be triangular planar, right? So its shape would be triangular planar, right? So these 3 hybrid orbitals would be having same energy and same shape, right? And the shape is your triangular planar. So whenever you have any molecule, right, in which the central atom is sp2 hybridized, then its shape would be triangular planar, right? So let's quickly take an example. We will take example of beryllium fluoride. We will take example of boron trifluoride, right? Let's take example of BF3, right? This is your boron trifluoride, and the electronic configuration of boron is, its atomic number for boron is, atomic number is 5, right? So its ground state electronic configuration would be 1s2, 2s2, right, 2px1, right? And when beryllium fluoride will form, when fluorine atoms will come close to boron atom, then energy would be released. That energy would be used to move this one electron from 2s orbital to 2py empty orbital, right? So excited state configuration would be 1s2, 2s2, 2px1, 2py1, right? Now these 3 orbitals, right, that have nearly same energy, right, because orbitals of same shell will undergo hybridization, right? So this 2s plus 2px plus 2py, right, that means 1s and 2p orbitals will undergo hybridization to form new set of 3 hybrid orbitals, new set of 3 sp2 hybrid orbitals, right? sp2 hybrid orbitals of boron, like this. like this, right? Now these three sp2 hybrid orbitals, right, that have now one electron, right, because this has one electron, s has one electron, 2px and 2py both have one electron, right? So all these have one electron, right? Now these three sp2 hybrid orbitals that have triangular planar shape will overlap with these three hybrid orbitals will overlap with boron, three fluorine atoms, like this, right, like this. This is your fluorine atom, right? Similarly here, this is your fluorine atom, right? So three fluorine atoms have overlapped, right? These, we know the electronic configuration of fluorine is this. It has one half filled 2pz orbital, right? So 2pz orbital of fluorine atom will overlap with sp2 hybrid orbital of boron, of this boron atom, right, to form, it would be like this, sp2 hybrid orbital of boron atom will undergo overlap. This overlap will occur. It will overlap with 2pz orbital of fluorine atom, right? This is the overlapping to form these three bonds, right? This is how bonding will take place in boron trifluoride, right? This is your sp2 hybridization. This is an example of sp2 hybridization, right? Now similarly, we have SP3 hybridization. This is your SP2 hybridization. Similarly, we have SP3 hybridization, right? An example of SP3 hybridization is your carbon, right? Carbon has electronic ground state electronic configuration 1s2, 2s2, 2px1, 2py1 and 2pz, right? Now 2pz 0. Now one electron, we will study its hybridization in this molecule, methane molecule, right? Now when this molecule will get formed, an electron would be shifted from 2s orbital to 2pz orbital, right? We have one electron now here and one here. Now this is your excited state electronic configuration where you have 2s, one 2s orbital and your three p orbitals, px, py, pz. Now these four orbitals, right, it is 2s plus 3 p orbitals, right? These are 3 p orbitals, 2px, 2py, 2pz will undergo hybridization to form set of, how many are these? 1s, 3p. So total 4 orbitals will undergo hybridization to form 4 set of hybrid orbitals, which would be sp3 hybrid orbitals, right, which will have same energy and shape, right, and orientation, right? So these hybrid orbitals would be directed, these are 4 hybrid orbitals which would be directed towards corners of a regular tetrahedron, right? It will look like this, right? This is how it will look like. Now these set of 4 hybrid orbitals will undergo overlap with these 1s. Electronic configuration of hydrogen is 1. So these 4 hybrid orbitals will undergo overlap with 1s orbital of hydrogen atom to form methane molecule, right? So whenever you have any compound that has central atom with sp3 hybridization, then its shape would be tetrahedral, right? These sp3 hybrid orbitals are directed towards the corners of a tetrahedron, right? So I hope all this is clear. In the next video lecture, we will take some more examples of these sp2 and sp3 hybrid